Live. Okay, here we go. So this was the third question on the 2010 exam. 2010 was kind of like, there you go, was a hallmark year for section 6.1 because, as I mentioned at the onset of the section, 4 of the 6 free response questions dealt with applications of accumulation, okay? So this was actually the third one, which was still a calculator back then. Nowadays, it's not. You have the first 2 with the calculator, and then the last 4 without a calculator. So they're kind of moving away from the calculator. Yeah. On average, 15 minutes per question. So you have 30 minutes to do 2 problems with the calculator, and then you put your calculator away, and then they give you 1 hour to do 4 problems. And you can manage your time within there on any problem. Okay, so you don't have to like stay on one problem for 15 and move on. All right, so this one was kind of exciting. It was a roller coaster problem. So keeping in the spirit of accumulation, what you have at any given moment is a combination of what you started with plus what you've accumulated since that time. What you've gained minus what you've lost. All right? So here we go. There are 700 people in line for a popular amusement park ride when the ride begins in the morning. How does that happen? How are there already 700 people in line when the park opens? Camp out, right? Yeah. They jump the fence. They're in there illegally. I don't know. Some parks like Disney, they open the front part of the park before they open the back part of the park or something like that. So for a popular ride, you can actually allow people to get there early to camp out. So whatever the reason, there's 700 people that are already in line when the ride begins operation. Once the ride begins operation, it accepts passengers until the park closes 8 hours later. It's not open that long, 8 hours. While there is a line, people move on to the ride at a rate of 800 people per hour, okay? So when there's a line, that means that they have enough people to put the ride through its maximum capacity level, okay, which is 800 people every hour. That's a variable or a constant? Constant, and it's a rate equation, right? The graph shows R of t, the rate at which people get to the ride. So they're coming to the ride, and then they're getting on the ride, which means they're getting out of the line. Time is measured in hours since the ride began. All right, so here's a little R of t. This is how fast they're getting to the ride, coming to the ride. They're getting on the ride at 800 people per hour, constant. They're getting to the ride at a variable rate, people per hour, and hours. So immediately, if you tell yourself, if I integrate, I'm going to be multiplying, and I'm going to get units of what? What's people per hour times hours? People. People, right? People per hour times hours is people. So if you find the areas under this curve, which you can because they're straight lines, you're going to get the number of people who have arrived at the ride during that time interval. Okay, sweet. Just kind of making sense of this graph. People are coming to the ride at 1,000 people per hour when it first opens. 2 hours later looks like it's the peak time for the ride, which would be at 10 a.m. That's when people are getting to the ride at 1,200 people per hour. Then it kind of tapers off, 400 people per hour. And look at this, right there before closing time, just before 8 o'clock, there's still that one person getting to the ride. That's me. That's when I ride those rides, at the very end, okay? Now, 800 is a very important number. Why is 800 an important number? That's how fast what? They're getting onto the ride. So right here, if you look at this right here, that's where the line 800, its horizontal, intersect that. That's at t equals 3. This is what we call the break-even point, right? At t equals 3 hours, they are actually getting to the line at the exact same rate as they're getting out of line and onto the ride. So should the line length be changing at this point in time? If they're getting to the ride at the exact same rate they're getting onto the ride, the line should not be changing. But notice before 3 hours, they're getting to the line faster they get on the ride. What's happening to the line length here before 3 hours? It's getting longer. And then after 3 hours, now they're getting on the ride faster than they're getting to the ride. That's when the line gets shorter. Okay? Very important. Ride gets longer before 3, exact same rate at 3, line gets shorter after 3. That's just kind of making sense of the problem. All right. What are they going to be asking us? Part A, how many people arrive at the ride between 0 and 3? Okay, show the computations that lead to your answer. How many people get to the ride? Well, here's the rate at which they get to a ride. They say between 2 and 3, so let me draw 2 vertical lines. There's 2, There's 3. Oops, try that again. We want the what then on this interval? What am I going to do? I'm going to find the area, yeah. And that's just one trapezoid, or you could do a triangle on top of a rectangle. So let's do the trapezoid. It's standing upright, so the 2 bases are vertical. 1,200 plus 800 is 2,000. The width is 1, so that's still 2,000. And what's half of 2,000? 1,000. So I'm going to write 1,000 in there. Okay, so now, notation. The function has a name. His name is lil r. So here we go. I'm going to always label my integrals. How many people arrived at the ride? So I'm going to say people. If you want to put arrived, just to kind of remind yourself, it's going to be the integral from 2 to 3 of little r of t dt. Yeah. Did I read that wrong? Oh, 0 to 3. My bad. Oh, it shouldn't be 2 to 3. I don't know why I read that it's 2 to 3 more than once. Okay, it is 0 to 3. So guess what we want? Thanks for catching that. I need all of this area, don't I? 0 to 3. So good thing we already found the one from 2 to 3. Read carefully. That's another trapezoid. The height is 1,200 plus 1,000, so now that's 2,200. The width is 2, so I'm going to take half of that. That's 1. And 1 times 2,200, that's 2,200. Whew, that was a close call. Read carefully. So now the people arrive. This makes more sense now. And I've done this problem so many times, I should have caught that myself. This would be then essentially how many people have arrived at the ride during the first 3 hours of operation. Do we want to add the 700 people to that were standing there before the park opened? No. So we're not adding the initial condition. This is just from 0 to 3, how many people got there. Okay, so now, since we've computed those 2 numbers in the graph, we just have to show us using them. So that's going to be 2,200 plus 1,000. And do you want to combine those? You want to go for it? I will. I'll take the risk. That's people. PPL. That's a good abbreviation. So 3,200 people got to the ride in the first 3 hours of the park's operation. And Kaufman saved that one. Okay. Thank you. Did we show the computations that led to our answer? Yes. What that essentially means is we have our areas. You don't have to show how you got those numbers. You can do that in your head if you want, or go off to the side and do it. But then those numbers appeared right here. So that's what they're going to be looking for. All right, part B. Is the number of people waiting in line to get on the ride increasing or decreasing between 2 and 3? Maybe that's where I was looking when I was scanning quickly. So now on this interval, let me use a different flavor. On the interval from 2 to 3, let's read that again. That was a lot of words. Is the number of people waiting in line to get on the ride increasing or decreasing? What's another way to rephrase that? Is the line getting shorter or longer between 2 and 3? We've already kind of thought about this. What's the answer? The line's still getting longer, right? Because the break-even point was when the rate is 800, which is exactly right at 3. So because little r of t is bigger than 800, which is the rate at which they're getting on the ride, the line's getting longer. So that would be the justification. So part B, you don't want to use their words. Is the number of people waiting in line to get on the ride increasing or decreasing? You can answer it directly, increasing. You don't have to say all that other stuff. Why? Because that's the only question they asked in part B. Okay? Increasing, and then it says justify, since, what? What's the easiest way to answer it? R of t is? R of t is greater than 800. I would probably add on this interval, just to strengthen the argument. And again, when you use the word this, that's a judicious use of the pronoun. Again, they only referred to one interval there, from 2 to 3 hours, and so there is no vague antecedent there, okay? So far, so good. Part C, at what time T is the line the longest? And then how many people are in the line at that time? Justify. Okay. When is the line going to be the longest? Do we kind of know what time that's going to be already just by looking at it? The line is going to still be getting longer as long as people are getting to the line faster than they're getting out of line, yes? At 3. Very good. At 3. Guess what most people said who got it wrong? 2. Because 2 is the maximum rate at which they're getting there. They said 2, but that's not the case. Because remember, 3 is where the rate of 800s are the same. So as long as it's bigger than 800, the line is still getting longer. So let's go ahead and answer that. At what time is the ride the longest? Justify your answers. Okay, at t equals 3 hours since. Now, how do you want to justify that? There's a couple of ways you could do it. This is looking for the local max or the absolute max? Absolute max. Very good. So there's a couple of ways to do it. You can either figure out the number of people. Let me abbreviate this. You could do the EVT, which is what we did the other day. You could do people in line at, and then you could say t equals 0 hours, t equals 3 hours, and then the right-in point would be t equals 8 hours. And then in this case, since I don't have a function for that, I would just do it like that instead of like p of 0, p of 3, p of 8. That's one way to do it. Or you could do it using the modified argument, which is the first derivative argument. That's probably what I would do. At t equals 3 hours since r of t is greater than 800 for all. That's what makes kind of like the first derivative argument is going to be since r is positive to the, or bigger than 800 to the left and less than to the right. But when we say for all t on the interval from 0 to 3 hours, and r of t is less than 800, it never goes back up. Less than 800 for all t from 3 to 8. So again, we're using the relevant domain. We're not just saying to the left of 3 and to the right of 3, or everywhere to the left of 3 and everywhere to the right of 3. We have an upper bound and a lower bound. The lower bound is 0 hours and the upper bound is 8 hours. Okay? Whenever you say for all, that turns it into a global maximum. Now, if that rate had come back up, let's say over here like at 5 o'clock, the afternoon spike, it went back above 800, I would actually have to use both those values where it crosses on the way up and crosses on the way down if I were going to be doing it this way. And then I really couldn't use that other argument either because it wouldn't be true. All right, so this would be the easiest way to justify it. And now we can figure out how many people are in line at that time. Well, we kind of can figure that out as well, right? How many people got to the line? We already figured that from 0 to 3. 3,200 people. So to figure out how many people in line, let's come up with a formula for that. At this time, there are, okay, who makes up people in the line? The people that get to the line, of course. What about the people who are out of line? Do they count? The people that were already there and got out, do they count? No. And what about the people who were standing there in the beginning? Do we need to take them into consideration? Did they ride? They rode. So what you need to do then is think about, okay, we're looking for a value at any given moment. So it's going to be how many people there were to start with, 700 to start with, that's your initial value, plus how many people got to the line, which was 3,200. And we can import that number, 3,200, straight from part A without even saying that, minus the people that got out of line to ride the ride. The number of people in line at any given moment is a function of what we started with plus what we've gained minus what we lost. That's the net accumulation idea. What you have at any given moment is what you started with plus what you've gained minus what you've lost. How are we going to figure out who we lost? Yeah, we're losing 800 people per hour, so you don't even need calculus for this. Most of the time you're setting up an integral here. It's just going to be 800 times how many hours? 3. That's it. Do we even need to simplify that? No, but if not, I'm going to put people on the end. Now, I'm kind of curious what that is. That's going to be 3,200 minus 2,400. That's 800 plus 700. That's 1,500 people. No bonus points for that, though. So that's the idea of accumulation. What you have at any given moment, and that's what they asked, how many people are in line there, what you started with, the initial condition, what you gained from set time, which we've already figured out, minus what you've lost. All right, sweet. And now, part D. This is kind of interesting. Write but do not solve. Okay, if you insist. An equation that involves an integral expression of r whose solution gives the earliest time t for which there's no longer a line for the ride. Okay, what we just did on part C was we determined how many people were in line at t equals 3. That's a concrete example, and this is so typical of College Board. What we're going to do on the next part is kind of do the same thing, but we're going to do it for an abstract general time t instead of t equals 3. So it just says write an integral equation. So we want to know how many people are in line, or what is the time where there's 0 people in line. So let's go ahead and write an equation, just like we did here, for the number of people in line at any given time t. We start with what? 700. Let me call that D. That's the people we started with. Plus, in general, how did we get our 3,200? We integrated the function r of t from when they opened 0 to, now we don't know what the time is, so we're going to call it t. Of r of what? Can we put r of t dt? No, we've done this before. Because we want t to be the variable. That's the time where there's nobody in line, and we don't know what it is. It's a variable. We're going to change the rt dt to rx dx, rm dm, anything besides t. So that's going to be, this will be the starting amount. This is how many people we've gained. And then now we need to say minus the number of people we lost, which is what? 800 times what? T, right? If we knew what T was, we'd be able to evaluate it. So this is how many people we lost. And now we want to know when that's equal to what? 0. Yeah. Let's back off instead of calling it 0. Sometimes they might not ask you to write an equation for when it's equal to 0. Sometimes they just say, write an equation for how many people are in line for any given value of t. So let's call that L of t. So now the number of people in line at time t for any value of t is the number of people we started with, 700, plus the people we've gained minus the people we lost. We open at 0. We want this to be t, right? So if this was like how many people are in line at 3, L of 3, that would be from 0 to 3, yes? That's why we have to change this variable. If I don't change r of t dt to r of something d something, then there is now confusion as to what your independent variable is. If you left it as r of t dt, then if I ask you what is L of 3, you might say the integral from 0 to 3 of r of 3 d3. And so we change it to anything so that there's no confusion. Remember, as long as the variables match, they could be anything. So we change it to, I like x. Anything works. And then minus 800t. So if you wanted to do this first, like on part C, and then if that makes more sense to you to do that, then on part C, here's what you're doing. What is L of 3? It's going to be 700 plus the integral from 0 to 3 of r of x dx minus 800 times 3. That's essentially what we answered on part C, but we did it intuitively. Of course, 0 to 3 is what they had us figure out on A. It's 3,200 minus 2,400. So if you're more comfortable doing that on part C, that's fine. Now on part D, all you have to do is set L of t equal to 0. So if you didn't do it that way, that's where on part D you would say, okay, started with 700, we're gaining in general 0 to whatever t is of that function, r of something, d something, minus, now this one has to go back to t, because whatever t is, if it was 5 hours, we want it to be 500, or 5 times 800, and now we set it equal to 0. So this is what you leave at part D. Okay, and that's it. You don't solve it. If you try to go beyond that, you're going to start losing points. Okay, so again, another application of integration. What you have at any given moment is what you started with, plus your net accumulation. Now, sometimes your net accumulation is one equation. In this case, it's two different scenarios. What we gained, and then minus, on our own, what we lost. Two separate things. All right, let's quickly look at the scoring guidelines so you can see where the points came from. Number 3, you got 2 points for number 1, one for the integral, one for the answer. So just the notation, 0 to 3 of r of t dt, got a point. Number 1, answer with reason. Number 3, identifying 3 as the correct answer, the number of people in line, and the justification. And of course, the justification is exactly what we said right here. Part D, you got 1 check for having 800t, 1 check for your integral. Notice they used s instead of x, and then 1 for the answer, which is basically remembering to add the 700 to it and set it equal to 0. So keep that in mind. Part C and Part D were very closely related. C was an actual specific time, 3, but doing the same process, and then D is going abstract for any time t. Sometimes they do it that way. Sometimes they flip it around. Sometimes they'll ask you to write the abstract equation first, and then the next part would be to actually use it, to evaluate it at a point. All right, scoring statistics out of 9. This is the first time you saw it, but if you saw something similar again in the future, hopefully you'd be more comfortable. Out of 9, this was question number 3. The average was only 2.19. So pretty low, 2.19 out of 9. Now, just for the record, I did make a mistake yesterday at the end of class. The baby zoo problem, I said it was example 5. I thought it was problem 5. It was actually question 2. Question 2. So from that same year, question 2 actually was 2.6. So these questions were asked consecutively on the actual AP exam. Baby elephant, amusement park. And they weren't doing so well on them. Less than 3, almost equal to 2. So keep that in mind. There's 9 points available, so you get as many of them as you can. And then you don't worry about the rest, right? Do your best, forget the rest. Any comments or questions about the amusement park problem? All right, moving on to the next. We're in here, kind of a shortened period till 3:10. No, 2:20. Good. All right, the next one. I don't know if we're going to finish this one. This was the first one on the entire test this year, and it was a calculator problem. The picture was not part of the original problem. I added that, okay? So here was the first one that they took. It almost sounds like it should be the start of maybe the English exam. There is no snow on Janet's driveway when snow begins to fall at midnight. Ooh, this is going to be a good story, right? From midnight to 9 a.m., snow accumulates on her driveway at a rate modeled by, okay, the story just went south, right? Now there's math involved. All right, so let's back up. There is no snow on Janet's driveway when snow begins to fall at midnight. Is that an initial condition? Yeah, at midnight, which corresponds to t equals 0, how much snow was there? 0 snow, right? Molecules, balls, whatever you measure it in. 0 snow, none, at t equals 0. Then, right at midnight, perfectly, almost like an orchestrated math problem, snow begins to fall at a variable rate modeled by this. And again, it's cubic feet per hour. So if you integrate that equation, you're going to get units of cubic feet. You're going to get how much snow fell over that time interval. Keep that in mind. T is measured in hours since midnight. Janet then starts removing snow at 6 a.m. She gave Mother Nature a 6-hour head start. How about that? And now Mother Janet, whose picture is here, gets out there and starts getting to work. The rate G of T, also in cubic feet per hour, at which Janet is removing snow from the driveway, is modeled by this. Janet is a piecewise function, okay? Mother Nature is variable. Janet is a machine, okay? So here we go. From 0 to 6, that's from midnight to 6 a.m., Janet's removing snow at what rate? 0. You think she's asleep inside? No, she's wide awake watching Mother Nature. All right, come on, Mother Nature. Giving you a 6-hour head start. Bring it on, Mother Nature. That's what she's doing. Her husband is sleeping. Make sure the driveway is clear when I get up in the morning. Jerk. All right, you start thinking about these things. Now, Janet gets out there at 6 a.m., and for a full hour, from 6 a.m. to 7 a.m., she is a boss machine removing snow at a constant rate of 125 cubic feet per hour, right? So in that 1 hour, how much snow did she remove? 125 cubic feet. Cool. She's human, after all, so for the next 2 hours, she kind of lost a little bit. Still pretty impressive, 108 cubic feet per hour, consistently for 2 hours. How much snow did she remove during that 2-hour period? 219, right? So the total amount of snow she removed, we already know, is 125 plus 219, right? Got it? So far, so good? All right, part A. How many cubic feet of snow accumulated on the driveway by 6 a.m.? I knew they were going to ask this. All right, so how much snow did Mother Nature? So label it snow. It's going to be the integral from 0 to 6 of what equation? F of t or G of t? F of t is Mother Nature, G of t is Mother Janet. So it's called F of t, and that's different from G of t. So all you have to do is put F of t there. If you want to put 7t e to the cosine of t, that's fine as well. Now this was a calculator question. So now we're going to go to the calculator. By the way, notice we didn't even really use the calculator much on that other one. I am in the wrong mode, so I'm going to come down here. I'm going to put Mother Nature's rate equation in y1. So that is 7x, the calculator always accepted as x, e to the cosine of x power. So that's second ln cosine of x close. Make sure you're in radian mode. You should have everything pegged to the left-hand side here. Now, we don't really need the graph, so I'm not going to worry about it. So once you have your setup, this is going to get points for your integral setup right here. You just go to your calculator, math 9, 0, that's midnight, 6 a.m. Mother Nature's rate equation, alpha trace, is in number 1 with respect to x. Go Mother Nature. You get 142.274 or 275 cubic feet. Remember, units are important. Now notice it said how many cubic feet of snow have accumulated. Yeah. Oh, alpha trace. If you hit the alpha green button, all of those top buttons have active links now, except the very last one. So if you click the wrong one, you could just use the directional pad left and right to find it. Now, notice it said accumulated, so we only use the rate equation. What if it said instead how much snow was on the driveway at 6 a.m.? Is that a different question than accumulated? In general, yes, it is, right? If it said how much snow was on the driveway at 6 a.m., you would take the 142.274 and add it to the amount of snow that was already there. But in this case, how much snow was there to begin with? 0 snow. So the difference between what is it at this moment versus how much have we accumulated over an interval. All right, so that's part A. Part B, find the rate of change of the volume of the snow at 8 a.m. Find the rate of change of the volume of the snow on the driveway at 8 a.m. Well, we have two rates that are competing at 8 a.m., right? Mother Nature and Mother Janet, okay? Mother Nature and Mother Janet. All we have to do is compare their rates. This will be part B. So how do we find the rate of Mother Nature at 8 a.m.? It's just F of 8. That's the rate equation. So F of 8, that's how much Mother Nature's throwing it down, and then minus Mother Janet is G of 8. Okay? If I subtract those two and that ends up being a positive number, who's winning the battle at 8 a.m.? Nature. But if that ends up being a negative number, then Mother Janet is winning, right? Okay, so that's all you have to show for your setup. Now, How are we going to figure out what f of 8 is? We're going to plug it in. How do we figure out what g of 8 is? I don't have g of t in my calculator because it's a piecewise function. So remember how we evaluate a piecewise function. At 8, we're using the middle piece, right? What's her rate at that moment? Oops, sorry. I'm doing it again. 1, 2, 3, 4, 5, 6, 7, 8. There we go. 8 is between 7 and 9. So what's her rate at 8 a.m.? 108. So I'm going to go ahead and say that's f of 8 minus 108. And now, from the home screen, I'm going to hit alpha trace. Everyone good with that? That's how you recall y. We have the rate equation in y1. If you open parentheses, type in an 8, and close it, now it evaluates it. It doesn't integrate it, doesn't differentiate it, just evaluates it. Minus 108. Hit enter. Perfect. I love this. This is a great story. What are the units of negative 59.582 or 583? It's a rate equation, so cubic feet per hour. Yeah, cubic feet per hour. All right, so because it's a negative number, g of 8 is bigger, which means Mother Nature's winning. So if you had to write a sentence, you would say at 8 a.m. or at t equals 8 hours, the amount of snow on the driveway is decreasing by 59.582 cubic feet per hour, and then you might put, go, Janet, go, right, after that. Would you be allowed to do that? Yeah, that's fine. So far, so good? Snow. Like Yankee Stadium the other day for the home opener. Let h of t represent, here we go. Let h of t represent the total amount of snow that Janet has removed at t hours. Express it as a piecewise function from 0 to 9. Let h of t represent the amount of snow Janet has removed from 0 to 9. Okay, and it's going to be a piecewise function. So this is the one that kind of tripped people up, but hopefully it won't trip you up. So h of t, it's going to be a piecewise function, so it's going to change on the same intervals where her rate changes. So if you want to kind of set that up, this is her rate, and we're trying to give you the amount of snow that has been removed. So much like the roller coaster problem, if you multiply her rate by the hours time that she's been shoveling at that rate, you're going to get the total amount of snow. All right, so the first one is easy. If she's shoveling at 0 cubic feet per hour, how much snow has she removed at that rate? 0. So that's 0, comma. All right. From 6 to 7, if she's shoveling at 125 cubic feet per hour, all you have to do is multiply her rate by the time that she's been shoveling at that rate. But do you want to just put T there? Well, let's try it. If you do H of 6, that would be how much snow has she removed at 6 a.m. If you come here and like, oh, use the middle one, you would do 125 times 6. Is that right? Has she been shoveling for 6 hours by 6 a.m.? No. So what you need to do is you need to adjust the T. Okay? She started shoveling at 6, so you need to say T minus 6. That's the tricky part there. Not tricky, but the catch. So now let's try it. Let's try it 6.5. That makes sense. At 6.5, she should be shoveling at that rate for a half hour. So H of 6.5, you'd come to the middle one. It's between 6 and 7. What's 6.5 minus 6? A half hour times 125. That'll work. All right, now for the next part. From 7 to 9, she has already shoveled for a full hour, hasn't she? And has removed how much? She's removed 125 plus anything additional that she's been shoveling at that new but still respectable and lower rate of 108. So I'll just put 108. And now it's going to be T minus what? 7. Good. Now if you want to try it out, try it at 8. At 8 hours, H of 8, how much snow has Janet removed at 8 a.m.? Well, you come down here, it's the bottom one. You're like, okay, she's already shoveled for a full hour, so 125 plus 8 minus 7 is 1. That's 1 additional hour at the new rate of 108. So there's your equation. The thing that a lot of students forgot were to modify the T based upon the upper bound of the previous one. And on this last one, they forgot to add the total amount that she's already removed in that previous time slot. Okay? Part D. How many cubic feet of snow are on the driveway at 9 a.m.? Here's the ultimate accumulation question. The amount of snow on the driveway at any given time is the amount of snow we started with, which is what? Let's go ahead and set it up. The snow is what we started with, which is 0. I'm going to go ahead and put it down just to account for it. Not that I forgot, but I added the initial amount of snow. Plus the amount that's been deposited, that's going to be the integral from 0 to 9 of r of t dt. We haven't found that number yet, so we're going to write it as an integral. And then minus the amount of snow that Janet has removed at 9 a.m., which, hey, you have two options now. If you trust your equation up here, you could just put h of 9 and then use this part right here. But if you're like, man, I didn't really get the previous one. It hornswoggled me. But I know that I can figure out intuitively how much snow Janet has removed by 9 a.m. Okay, here are her rates. 0 to 6, no rate, so nothing. 6 to 7, that's a full hour at 125, so that's 125. Plus, at the end of the next 2 hours, that's an additional 108 times 2, so that'd be 219. We actually had that conversation before we started. That would be the exact same thing you got if you had h of 9 right here and then plugged in. 125 plus 108 times 2, okay? Now, can we leave it like that, or do we have to evaluate it? Did it say set up but do not evaluate it? Yeah. 216. Thank you. 108 plus 108 is 216. I will not be there on the actual exam to mess you up. So that should be comforting to you. Okay. We have to evaluate this because it didn't say just set it up and not evaluate it. So no big deal. Here we go from the home screen. Let's flush. 0 plus math 9 from 0 to 9. Where is our rate equation for Mother Nature? Y1, alpha trace, number 1, with respect to x, and then minus parentheses, I'm not going to trust my math, 125 plus 108 times 2. Look at that. I don't trust my math at all. 26.334 or 335 cubic feet. So ultimately, at the end, by 9 a.m., Janet did not remove all of the snow, but that's fine. She made enough for her husband to get out because she's tolerant of him, but she wants to let Mother Nature have a feeling of victory so that Mother Nature will come back again next time and compete, okay? So there's like a minute left. As you're putting that away, I just want to go ahead and run through the scoring guidelines. Turn in your calculator, maybe clear it out so the next person doesn't have anything in there. All right, real quickly, you got 2 points for the first one for the integral, 1 for the answer, 1 for the next part. You got 3 parts for part C. That's the one where some students messed up, but notice it's real easy to get the first check. How much snow has she removed in the first 6 hours? 0. That was worth 1 check. So if you messed up on the adjustments, you're only missing 2 out of maybe 9, so you're getting 7 out of 9. And then the last one, 1 for the integral, 1 for the h of 9, which was her amount, and then 1 for the total. All right? Let's see what the scoring statistics are. Look at that one, 3.67. The first one's a little bit better because students are fresher. Yeah. Y'all can go. A few seconds were left, but that's all right. Yeah.